Hey, hi everyone. Good morning.
Good morning, Shiva.
Okay, so on Saturday we discussed about this hypothesis testing. Let's have a quick revision on this, and then we'll talk about other topics. Um, so here we are talking about one sample test, guys. Okay, so whatever we have discussed on Saturday, that is one sample test. So what is one sample test is here. So here in one sample test, we will have some information about the population and then we will infer something about that population by only selecting only one sample. Okay, and with one sample, we are here calculating the mean of that sample, and based on this mean, we are inferring about the population. So now this whole hypothesis testing, where we are just using only one single sample, is known as one sample test. So here we are talking about population mean. If any information is provided related to the population, and if that is mean, then we go ahead with this population mean test. And in this scenario, we have, in this case, we have two scenarios. One is like where sigma is known and where sigma is unknown. So on Saturday, we discussed about this particular scenario where sigma is known. And we know that wherever we have the information about the sigma related to the population, we go and use the Z distribution. We use the Z distribution. And we understand how to develop the hypothesis. We develop the hypothesis by considering whether our actual population mean, whether it is less than equal to your given population mean, or whether it is greater than equal to given population mean, or whether it is equal to given population mean. And then accordingly, we formulate the null hypothesis and alternate hypothesis. By looking at the alternate hypothesis, we will arrive whether it is a lower tail test or a upper tail test, or it is a two tail test. If it is alternate hypothesis, if we find this greater than sign, then it is considered as upper tail test. When it is less than sign, then it is a low tail test. If it is like not equal to, then it is a two tail test. Okay, so going forward, yeah. So we discussed about lower tail test in the last class. Now let's talk about the two tail test, for this population. So before getting into this example, if anybody has any question, then please do let me know. Okay. So for example, for the two tail test, here the example is we are assuming that the sample of 30 milk cartons. So whenever we get this kind of information, we can clearly define that sample size is 30, where n is equal to 30. It provides a sample mean of 505 ml. So this is x bar. The population standard deviation is believed to be 10 ml. So this is sigma, okay, which is given to us. Then we have to perform a hypothesis test at 0.03 levels of significance. So it is what? This is alpha. Population mean is given, which is 500 ml. So it is the given population mean, which is equal to mu zero. And to help determine whether the filling process should continue operating or to be stopped or corrected. So what it is saying that here they are just interested whether they are meeting this particular value or not. So here your null hypothesis says that your actual mu is equal to 500 ml. And what we have to prove is it is not equal to 500 ml. So in your sample, it is coming out to be 505. Now we will go and statistically test that, okay, it is not equal to my given population mean, which is 500 ml. Now, in this case, there is no less than or equal to, there is no less than or greater than. Here we are talking about not equal to 500 ml. So here it qualifies for two-tail test. What is two-tail test? We have discussed in the last class that if your given mu zero is this, now we have to prove statistically that this particular actual mu, which we will check whether it coincides with mu zero statistically or not. So it may be less than or it may be greater than. Now that's something we will go and test it through this two-tail test. Everything will remain the same except one. In the two-tail test, we will consider alpha by 2 instead of alpha. And that we have also kind of discussed during the confidence interval. So here we are saying that there is 3% chance or 3% error which we can consider. So 3% error, in this 3% error, this mu can be less than equal to less than mu zero, or this mu could be greater than mu zero. So that means this particular error could be on either side of the mu zero. So what we have to do is we have to divide this alpha by 2, stating that there could be an equal chance of error on the either side. So we are taking alpha by 2 here and alpha by 2 here also. And now instead of comparing with alpha, now here we will compare with the alpha by 2. Now let's go step by step. So here with this particular example, we know that sample size is given, sample mean is given, the population mean is given, standard deviation is given, significance level is given. So these are all the given values. With these given values, we will go and this hypothesis testing, and here we will use the p-value. Here we will go only with p-value approach, just to avoid confusion. And in the industry also, usually we only go with p-value approach rather than going with critical value approach or the confidence level approach. So firstly, what we have to do is, now this is my hypothesis which we have developed, where my null hypothesis states that this particular actual population mu is equal to 500, and here alternate hypothesis states that it is not equal to 500. Now the second step is all about finding out the Z score or test statistics. We call it as a test statistics because this is something we are calculating with the help of sample. So whatever parameters or whatever values or measures you calculate from the sample is considered as test statistics. So this is the formula, the same formula which we have seen in the last class. It's x bar minus mu divided by sigma by root L. So all these values are given to us. We will substitute all those values and calculate the Z value. Now, for this Z value, we will go and find out the probability value. For that, what we will do, we will refer to the Z distribution. And in the Z distribution, you know that by referring to the Z table or by using Python, if we give the Z score for that particular Z score, it will give us the probability. Now, let's suppose in this Z distribution, this 2.74 lies somewhere here. It's 2.74. And here in the two-tail test, what we are doing is we are dividing this alpha on either side. Okay. In one tail test, the entire error was on the either side of the tail. Okay, either it was on the lower side or on the upper side, because in those scenarios, my alternate hypothesis was either greater than or less than. But in this case, it is not equal. So that means the error could be on the left-hand side or could be on the right-hand side. And here we will divide this alpha by 2 because we are referring to the Z distribution, which is a symmetrical distribution. So here we are not getting bias to any one side. So here we are dividing the error on both the sides equally. So here we are saying there could be 1.5% chance of error on the left hand side, that it may your actual mean could be less than 500, or there is 1.5% on the right hand side, whether if actual mean is greater than 500. So overall, the error is 3%. Okay. So what would be the confidence level here? It is 97%. So at this particular value, we will go and find out the probability. Okay. And that probability we have to compare with alpha by 2. If this probability is less than alpha by 2, then we can go and reject the null hypothesis. Or else what you can do is you multiply this probability by 2 and then compare it with by alpha. So 2 times of probability will be considered as p-value, and that p-value is considered as alpha. I will again repeat. In two-tailed test, whatever test statistics you will calculate, based on that test statistics, you have to go and find out the probability from the Z distribution. That probability you have to compare with alpha by 2, not by alpha. In two-tailed test, this is very, very important thing which we have to keep it in mind and you have to remember. You will compare with alpha by 2. Or else you calculate the p-value. P-value would be nothing but 2 times of this probability. That would be your p-value, and then you will compare with alpha. So now let's go and see that how it happens. So now here the z is coming out to be 2.74. And for 2.74, this is my probability. So this probability I have multiplied with 2, and now this is my p-value. Now this p-value I'll compare with my alpha value, which is 0.03. So now here you see this particular p-value is, yes, it is less than 0.03. So we can go and reject the null hypothesis. Now how we will infer this test? We say that there is no sufficient statistical evidence to infer that null hypothesis is true. So depending on the way we have developed the hypothesis and we understand the problem, accordingly we have to write down the inference. Here we are saying there is no statistical evidence to infer that my null hypothesis is true. That's the reason we are rejecting that null hypothesis and we are going with the alternate hypothesis. So what the null hypothesis states is, it states that the mean filling um, quantity is equal to your 500 ml. And we are going with the statement that this particular mean filling quantity is not 500 ml. So here the statement is not whether it is less than or whether it is greater than. Here we are just saying that this particular standard is not being maintained and that we are telling it by significance level of 0.3% or confidence level of 97%. I'll take a pause. Let me know if anybody has any question.
Sir, in the fourth step, we have done 1 minus 2 into 1 minus.
Anybody wants to answer this question? Why we are doing 1 minus? See here we have discussed like it is 2.74, it is on the right hand side. To find out this particular probability, how you will calculate? We know that with the Z table or even in Python, if for a particular Z value, if you want to find out the probability, it will give us the left hand side of the problem. So which is coming out to be 0.9969. So to find out this particular probability on the right hand side, because this is something only we have to compare with alpha by 2, right? So for that, we will do 1 minus 0.996. The entire area under the curve is 1. So to calculate this particular region, we will subtract this part, okay, from the entire area, which is equal to 1. So that is this. So either this part you compare with alpha by 2 or you multiply by 2 and then compare with alpha. Understood?
Yes, sir.
Okay. So just understand whenever the values are positive, the Z value, I'll give you a tip here. Whenever the Z value is positive, so that means it is falling on the right-hand side of the mean. So for the Z value, what is the mean? Mean is equal to 0 and standard deviation is equal to 1. So whenever the Z value is positive, that means we are talking about the right hand side region. Whenever the Z is negative, that means we are talking on the left hand side. For the negative values, we need not to do anything because the Z tables or the Python functions, they will give the left hand side of the region. But for on the right hand side, if the Z are positive, whatever probabilities we are getting, we will subtract that by 1, to find out the right hand side of the problem. Okay, just remember that here, that thing when you are finding out the problems. Clear? So quickly revise, let's revise. Okay, let's suppose this is my null hypothesis and this is my alternate hypothesis. So which tail test it is, guys? This one? Hello? Which tail test is this if my hypothesis is like this? If my null hypothesis states that mu is greater than less than equal to mu zero and alternate hypothesis says that mu is greater than mu zero. As I mentioned, you need to look at this particular sign. If it is greater than, then it will become a upper tail test, right? If it is less than equal to mu zero, your alternate hypothesis, then it is a lower tail test. If your alternate hypothesis is not equal to mu zero, then it becomes your two-tail test. Is this part clear, everyone? Please acknowledge, guys. This is important. I need to know whether you are getting this one. This part is clear?
Yes.
Okay. For the upper tail test, okay, you need to, in a distribution, you need to calculate the right-hand side of the region. So for that, whatever probability you will get, you have to subtract that probability, from 1, to calculate the p-value. In the lower tail test, it's about the left-hand side of the probability, which itself will be the p-value. Here the p-value would be 1 minus of probability of this particular z value, pz. Here p-value would be probability of z. That's all. Here, based on whatever direction it is coming, you have to accordingly take the call. Either, z value could be negative here or could be positive here. It could be anything. If it is negative, then just directly calculate the pz and multiply that with 2. If it is positive, then you multiply this 1 minus 1. Now that would become your p-value. And that p-value, you have to compare with the alpha. So this always remember, guys, p-value you have to compare with alpha. And if it is less than alpha, then you have to go and reject your null hypothesis. See, here these statements are very important. We say reject null hypothesis. We will not say we are accepting null hypothesis. Okay, so even in the court, okay, the judge will mention like this only. With the evidence, we fail to prove them that he is innocent. He will not say that, okay, he will culprit. So the sentences, they will put it in that way. So here also we'll say that, okay, with the no sufficient statistical evidences, we infer that or we cannot go with null hypothesis. We cannot accept null hypothesis or we reject the null hypothesis. Here, never we'll say accept. In statistics, we never use accept word. We'll say we fail to reject or we reject null hypothesis. These are the two terms, which we will use in statistics. Okay. So again, I'll take a pause. Let me know if anybody has any questions on this. Okay. So if no questions, then let's move forward. All these things we have discussed. Now, the second scenario where the sigma is unknown. The sigma is unknown. We instead of Z distribution, we go with T distribution. So the previous test, whatever we have done, there the sigma was known to us, and we are going with Z distribution. And those kind of hypothesis test is called as Z test. All those tests we call it as Z test. Here, where sigma is unknown to us, here we will go and perform the T test. Rest everything will be the same, only the distribution will change. Instead of Z distribution, here we refer to the T distribution. And the formula is kind of similar. Instead of sigma, because the sigma is known as population parameter, the equivalent to this population parameter in the sample is considered as S. S is the sample standard deviation. So instead of using sigma, we will just use S. Other than that, the entire formula is the same. So now this T score is nothing, it is called as test statistics. And this is important, guys. You should remember where to use T distribution, where to use Z distribution. Okay. And here, one more term get added, which we have already discussed during our confidence interval, which is degrees of freedom. Degrees of freedom is nothing but the sample size minus 1. So when we are referring to the T distribution, along with the test statistics of T score, we also consider degrees of freedom. Then accordingly, we go and uh, identify the probabilities based on that score. Okay, so here again, you will find uh, the same three different scenarios, the where your null hypothesis could be greater than equal to mu zero. Here, my alternate hypothesis would be just opposite to this, which is less than equal to mu zero. In this case, it would be mu is greater than mu zero. And in this case, my alternate hypothesis would be mu not equal to mu zero. So this would be my lower tail test. This would be my upper tail test. This would be my two tail test. Okay. So only the scoring part would change. Rest everything will be the same. Now let's go and look at this example. So here it is a one-tail test about a population mean when sigma is unknown to us. If this is unknown, then that means we have to go with a T distribution. For example, in an ice cream parlor at IIT Roorkee, the following data represent the number of ice creams sold in 20 days. So this is my sample size, 20 days. So 20 days sales, they have kind of collected. So these are the number of ice creams sold for 10 days, and this is for another 10 days. So overall 20 days. Now the here they have developed the hypothesis for you. They are saying the null hypothesis says that the actual average sales per day is considered as less than equal to 10. Okay. So what is my alternate hypothesis would be just opposite to this, which will be greater than equal to 10, which is my mu zero. So this is my alternate hypothesis, and they have also given the alpha value, which is 0.05. In industry, the standard practice is if alpha is not given, then you can go ahead and consider it as 0.05. So 5% alpha is industry accepted value, okay, if it is not provided. Now, this is your given data. Okay. I'll tell you, how we can do it in Python, but just understand the concept. So now this is my distribution. Okay. Firstly, I'll go and calculate the test statistics at that and what is the alternate hypothesis? Alternate hypothesis says that it is greater than 10. Okay. So if it's greater than 10, it is an upper tail test. Now I have to look out for the probability in the upper tail. Okay. So here comes my t-score. This is my t-score. And at this t-score, uh, I will go and find out the p-value, which is the probability value. And that probability value I'll compare with this alpha. Uh, so here, if you see in this, how you can do it with in Python. So this is my data. This is my array or list in which I have these 20 data points for 20 days. So these are the sales of each day. Now you need not to go and calculate the mean. You need not to go and calculate the t-score, nothing. Okay. You just pass this entire data to the function of in Python, and it will give all the information to you. Okay. So from this particular sample, it will automatically calculate the sample mean. It will automatically calculate the sample standard deviation. So what all is left if you see this particular formula? Even this sample size can also be calculated through this data, right? It will just take the count of all the numbers, and that will become my n. So all these three values in the backend automatically will be calculated based on this particular list. So this is my sample. The only thing which I need to pass extra is this mu, and this is the uh, population mean at which I have to compare with. So which is equal to 10. So I will use in the stats library, I will go with this particular function t-test underscore one sample. Whatever we are doing, we are considering only one sample. And that one sample we are using to infer about the population. So here we are saying t-test underscore one sample. We are passing this entire list, and we are passing this mu on mu, with which we need to compare this X bar or sample mean. And now it will give me the output as test statistics. This is my test statistics or t-score, which is this, and this is my p-value. Okay. So this is my p-value. This, if it is a one-tail test, you directly compare with the alpha value. If it is a two-tail test, then you divide this p-value by 2 and then compare with alpha by 2, or else you multiply this p-value by 2 and then compare with the alpha value. Okay. So based on uh, based on your use case, based on the problem you're solving, accordingly, you have to go and use the appropriate alpha value to compare. So yeah, so nothing change. It's almost the same. The only thing is like instead of Z distribution, we are going with a T distribution. In Python, we will go through the Python codes. So you'll see that with one single line of code, you can perform this hypothesis testing. Just you need to pass the data and you have to pass the uh, uh, mean value, and accordingly it will do. Okay, now moving to another different kind of test known as proportion. Now we have discussed that for a population, we infer for three different parameters. One is the mean, which is represented by mu. Another is p, which is proportion, and the another parameters are related to the variance or dispersion, either standard deviation or the variance. So these are the three parameters for which we need to do some kind of inferencing. So whatever we have done so far, that was related to the mean, where the somebody was giving some information about the population mean, and I am going and testing and verifying it by sample. So in sample, equivalent to mu is denoted as X bar. So this X bar I'm using, and I'm considering the variance. I'm considering the standard deviation. The population standard deviation is giving, then I'm going with the Z-test. If it is not, then I'm considering the sample standard deviation. I'm going with the t-test, and then I'm inferring about these population parameters. Okay, either I'm accepting it or I'm rejecting it. Now we will talk about this population proportion. which is denoted by P. So for this, we have to refer to a sample proportion, which is P hat, denoted as P hat. Now, what is this proportion? So proportion, you know about it, right? So what is the representation of a particular category inside a proportion, inside the population is denoted as a proportion. So for example, percentage of males or percentage of defects or percentage of uh, uh, cars or whatever segment, okay, or percentage of a particular product segment. So all that thing can be called as proportion. So here we are going to test the proportion of uh, uh, any particular category in the population. So once we discuss about the example, you will understand. So before that, you know, let's see what kind of null and alternate hypothesis we can develop for this population proportion. Again, it would be almost the same. Instead of mu, we are going to use P here. That's all. So here, if alternate hypothesis states that your actual proportion is less than this P0, then it will become a one-tailed or lower-tailed test. If it is greater than, then it is upper-tailed test. If it is not equal to, then it is a two-tailed test. So that's how you formulate your hypothesis. Once the hypothesis is formulated, now here we do not have multiple scenarios as we have it for population mean test. Here we will go with only one single distribution, that is Z distribution. No confusion. Okay. So no multiple scenarios. If we are going with the population proportion, by default, we have to go with the Z distribution. Here the formula for Z distribution is Z test statistics is Z equal to P bar or P hat minus P0 divided by variance. So the standard deviation. The standard deviation formula is for proportion is this. Okay, let's understand this. For example, somebody is stating that in a particular plant there is only in a day they get only 20% defects. Okay, so defects proportion is 20%, or else in ratio we can call it as 0.2. So what is the ratio of non-defects? It will become 1 minus 0.2, which is 0.8. Okay, so this is your P0 and this will become 1 minus P0, or else you can call it as Q0. Okay. Now, test statistics, how you will calculate is you will take this Z. Somebody has states P0. Now I cannot go and check the entire population. What I will do is I'll derive a small sample, and in this sample I will calculate how many defects are there. Okay, so and that I will denote it as by P hat. So that P hat I will use it for calculating the test statistics, and I'll compare with this P0 and see whether it is greater or lesser. If it is this P hat is greater, then it will become my upper tail test. If it is lower, then it will be negative. Z value would be negative. Then I have to perform the lower tail test divided by the sigma. Now sigma is denoted by is the multiplication of 1 minus P0 and P0. So the proportion of having that particular object and the proportion of not having that object, you will take the dot product of that. Okay, so P0 into 1 minus P0 divided by sample size. And then you will take the square root. So this is the variance. If you want to go with the standard deviation, then you have to take the square root of the variance. And that will become my sigma. So just you need to substitute that values, okay, into this particular equation, and you can able to calculate the test statistics. Once you calculate the test statistics, rest of the steps will be the same. That test statistics you have to go and check on in the Z distribution. You have to find out the probability, and that probability you have to compare with the alpha value. Here, before even attempting for this hypothesis testing, you have to go and check these assumptions are fulfilled or not. Here we are saying if you multiply the sample size with proportion, let's suppose I have, uh, this is my sample. in my sample, I got 30% defected and 70% non-defected. And the sample size is, let's suppose, n equal to 100. So here the assumption is that n into p and n into 1 minus p should be greater than equal to 5. It should not be very small minority class. Minimum there has to be a 5 observations. So in this case, if I go 100 into zero point 0.3, then it is like 30 units. And here it's 100 into zero point 0.7, then it is 70. So in and all, it is total is 100. So in this case, both these assumptions are meeting, so I can go and perform this test. If I have only sample size is 10, let's suppose, or the proportion is, let's suppose, 0.001, in that case, one of these assumptions will not be met. And in that case, you should not go and perform this hypothesis testing. In that case, whatever decision you will make may go wrong. Okay, so that's the check you have to take. If in your sample a particular proportion is not represented fairly, then you should not go and perform this test. You should go and collect more observations and make sure that minimum observation in each of the categories should be greater than equal to 5. Okay, so now, so we will go with this p-value. So we will go and calculate the p-value. How we will calculate the p-value? Simply by calculating the test statistics, z-test, and then referring to the z distribution. And with the z distribution, we'll go and calculate the p-value. Simple. Once we calculate the p-value, we'll go and compare with the alpha value. If it is less or equal to alpha, we will go and reject the null hypothesis. This thing you should remember even when you are sleeping, guys. So somebody asks you if p-value is less than alpha, your answer should be yes. If it is less, then we should go and reject the null hypothesis. Okay. Or else you can consider it like if p-value is less than alpha, then you have to go with alternate hypothesis. If p-value is greater than alpha, then you have to go with null hypothesis. Okay. This thing you please remember, because even in the machine learning, even in various kind of analysis, wherever we are talking about the p-value, this will come into picture, where we compare with the alpha and we have to make a decisions. All right, so critical value will not cover. Let's take an example. This is a very common, everyone will relate to it. For a New Year's week, the city traffic police claimed that 50% of the accidents would be caused by drunken driving. Okay. A sample of 120 accidents. So this is something what this traffic police is claiming for. So what this 50% is nothing but your capital P. It is telling on about the entire population. So that means for entire city. They're saying that 50% on this particular eve of New Year, yeah, 50% of the accidents are because of this drunken driving. So here the P is 0.5. Now somebody has to validate whatever they are saying, whether it is valid or not. So here we are going and performing this sample test. And here we are just taking only one sample. And that's the reason it is called as one sample test. Here they have collected 120 accidents details. And in those accident details, they found that 67 were caused by drunk driver. Okay. Now they are saying use this data to test the traffic police claim at alpha equal to 0.05. Now we'll go with the p-value. So firstly, we will go and determine the hypothesis. Okay, whether it is true or not true. This is what we are claiming. We have to find out. Again, it could be any of the case. Here we are just checking whether the claim is true or not true. In that case, we'll go with the two-tailed test. If you have to explicitly, you have to try to prove that okay, accidents are less than zero point 0.5, then you have to go and perform the lower tail. If you have to prove that whether the accident is greater than 0.5, then you have to go and perform the upper tail. So in this case, it is just proving whether their claim is true or not true. So here my null hypothesis would be this P, which is my actual proportion, population proportion. It is equal to zero point 0.5, which they are claiming. And my alternate hypothesis states that this P is not equal to zero point 0.5. Okay. Here my alpha is 5%. Here I will go and calculate the Z score or test statistics by this particular formula, which we have just seen. First, we'll go and calculate the sigma. Sigma is nothing but the product of these two, P0 into 1 minus P0, which is zero point 0.5 into 1 minus zero point 0.5 divided by the sample size, 120. So this is my sigma. So as it is, we are calling it as sigma, we are using this population proportion here, which is given in my problem. Okay, we are not going with a sample proportion. We are going with a population proportion. So with this, we can able to calculate the sigma. Now we will go and substitute those values into this formula, which is p hat or p bar. Okay. In some of the books, it is denoted as p bar. Some of the books, it is denoted as p bar. So this p bar minus p0. So p bar, which we can calculate. So it has been given that out of 120 randomly selected accidents, 67 accidents has been uh, caused because of drunk driving. Okay, so what is the proportion of drunk driving cases? It would be 67 divided by 120 minus this is given to us divided by sigma. So we will get the Z value. So this is my Z value, and this Z value is falling on my right hand side of the distribution, which is 1.28. Now I have to go and find out this particular region. Okay. Now with this, it is clear it is a two-tailed test. So two-tailed test means whatever probability I will get it at this particular Z value, or either I can compare with alpha by 2, or else whatever probability I will get for 1.28, I will multiply by 2 and then I will compare with alpha. So this you have to keep it in mind when you are talking about two-tailed test. So now I will go and find out the p-value. So p-value, as it is a upper tail test. So what I'm doing, whatever probability I'm finding out at p1 minus 2, basically I have to subtract it by 1 and then I have to multiply by 2. Okay. So this is something we are doing it here. So 2 into 1 minus 0.8997. So overall p-value is coming out to be 0.2006. Now this p-value is greater than your alpha value, which is 0.05. So if it is greater than what you can do, we cannot reject the null hypothesis. If it is less, then only we can reject the null hypothesis. So here, as we cannot reject the null hypothesis, we have to agree to this particular claim or whatever traffic police or department they are saying, we have to agree to it. Okay. So I'll take a pause. Let me know if this is clear on the proportion. So sorry. Yeah, so I was talking on mute. I'm so sorry. So here I'm taking only one single example for the two tail test. I hope you know you can perform the lower tail test and upper tail test. Okay. So go through the recording and again. It's simple actually, but it's sometimes it confuses us because all of the things we are discussing at the same time. So I don't want to give you multiple scenarios and confuse you further. Just put it separately, like lower tail test, upper tail test, and two tail test. How we can perform for population, how we can perform for population mean, how we can perform for population proportion. But the sequencing would be the same. Only the formula for calculating the test statistics will differ. If we are going with the population mean with sigma known, then we go with the Z score. If we are going with sigma unknown scenario, then we have to go with the T score. If we are going with the population proportion, we have to go with the Z score only. For population proportion, we do not have any scenarios. We generally consider only Z distribution. And we know that what is the formula of test statistics for all these three different scenarios, right? You just nicely create your notes. Okay, go through this and create your notes. And once you put it in the paper on the paper, I think it will be much clearer for you guys. Okay, you're good. So usually, apart from any pharmaceutical companies or food manufacturing companies, usually these kind of tests are very rarely being performed. So if you go to any pharmaceutical company, there it is heavily done. Okay, these kind of tests because you know, right? They go through multiple clinical trials. They generate a lot of samples. Okay, and then they have to perform some tests, you know, to take the decision based on those experiments. Even in manufacturing company where they have to uh, continuously monitor the process, the quality. There also these hypothesis testings are performed, frequently. But other than that, if you refer to any other businesses, any other function, so it is not done that much. But however, these hypothesis testing, we will also use it in machine learning algorithms to check whether my model is significant or not. Whether all the attributes of the model and all the parameters of the model, they are significant or not. So we will discuss about this hypothesis testing there. There you will see that the same concepts are used for different purpose. Okay, so I will not explain you now. We will discuss then only. So there we have to do something else. There we have to take decision something else related to the parameters which we are using for predictions. So for that we'll perform the test. Okay. But here I'm talking all the business use cases, which uh, which you may come across. Hold on a second. Yeah. I will talk about two samples. So see, usually when we consider any data, we will come across with only two different types of variables. One is like continuous variable, which is numerical column, and second is your categorical column. So for categorical column, usually we calculate the proportion. For the numerical column, we generally go and calculate the mean. So we understood if it is like continuous column, what test we have to do, and for categorical column, what test we have to perform. Now let's understand about these two sample test. Now what is this two sample test? In one sample test, again, I will recap. For one sample test, we are take what we are doing is we are taking one sample and then based on that we are inferring about the population and some information of the population is given. But in the two sample test, it is a kind of a scenario where you have two samples which you have collected from two different populations. This is population one, this is population two, and then you have derived the samples from these two population. Let's call it as S1 and S2. Okay, so this S1 and S2 you will compare whether those are statistically similar or they are not similar. Again, here the hypothesis would be, for example, if you are going with a continuous variable, here it would be x1 bar and here it is x2 bar. Now your null hypothesis could be this x1 bar is greater than x2 bar. Alternate hypothesis would be x1 bar less than x2 bar. So like that, you can have again three scenarios. Okay, and based on that, you can decide which tail test to accept. Okay. So here what we are doing is we are comparing the two samples. Now, for example, now I want to compare whether I have two plants. Okay, one is in Hyderabad, other one is in Bangalore. And I want to see that whether my quality standard in both the plants are same or whether one is greater or one another is greater. That's something I want to evaluate. So I cannot go and take the entire data and perform that particular test, right? So I'll go to the Hyderabad plant, I'll take some sample. I'll go to the Bangalore plant, I'll take some sample. So in that case, I will have two samples. Now, based on those two samples, I will go and measure the average quality of the product. It could be whatever, measure you want to consider. So for example, measure of impurity in your microbiome. So I will, for all the objects which I have considered in my sample, I will measure the impurity levels. And that I will take the mean of all the objects which I have selected in my sample. So that would be for Hyderabad plant, it would be X1 bar. For Bangalore plant, it would be X2 bar. Now, based on what I want to prove, I will accordingly I'll develop my hypothesis. If I have to prove that on both the sides the quality levels are same, so it is equal to. Okay, then I will define my null hypothesis like this, and my alternate hypothesis will be just opposite to this. Yep. And I will state it as x1 bar is not equal to x2 bar. Now this will become my two-tail test. See, approach is again the same. First, you develop the hypothesis, identify which tail test it is. Third, you go and calculate the test statistics. After calculating the test statistics, now you have to go and refer to the distribution to calculate the probability. And that probability you have to go and compare with the alpha rho. And based on that comparison, you have to make the decision whether you have to go with null hypothesis or whether you have to go with the alternate hypothesis. The only difference you will find is the formula of calculating the test statistics. So you have seen, right, for all those three scenarios which we have discussed in the before this, they have a different formula, okay, of test statistics, and even the distribution accordingly. We are selecting, for calculating the properties. Here also in the two sample test is the same. Your formula for calculating test statistics will differ. Okay, that's all. Remaining the approach will be the same. Those 4 and 5 tests, 5 steps. So for example, here is this again, it's the same representation. I have population one and population. From the population one, I have taken this particular sample and the sample mean is x1 bar. From here, population two, I have taken another sample. Here it is x2 bar. So this x1 bar will have some kind of distribution, population distribution. This x2 bar will have some kind of population distribution. Now I have to go and see whether these two distributions are the same or not. So for that, what I can do is I'll take the difference of these two distributions and see whether it is equal to 0 or not equal to 0. If it is equal to 0, that means these two distributions are same. That's the reason it is kind of giving me as 0. If it is one distribution is greater than another distribution, then you will get either positive or negative values. Okay. So let's go and see that how many different scenarios of two sample test we may see when we talk about mean test. So if we are talking about two samples, x1 and x2, and these two samples are continuous variables, then we can go and calculate the x1 bar and x2 bar. Now this will become the mean test. These are nothing but the means, right? Sample means. So we call it as a mean test. Now there are multiple scenarios, okay, for this. If we have the information about the population standard deviation or the population variances, then that is one scenario. If the population variances are unknown to us, then that is a different scenario. In that again, there are multiple two another sub scenarios. Okay. So first let's focus on this and we will come on this. Let's suppose my population variances are known to me. If by default, wherever you have the information about the population variance, then directly go and refer with that Z distribution. There you have to go and find out the we call it as a Z score or Z tests statistics. So now we'll take this scenario, and now let's suppose we are talking about independent samples again. Okay, so in this independent or dependent samples will come in this particular scenario a lot, but in this particular scenario where my population variances are known to me, we generally consider that these two populations are independent. So for example, the samples are randomly and independently drawn. So that's the reason they are known as independent samples. And both the population distributions are normal because in that way only we can consider that they both are following some kind of we can refer to the Z distribution. So these are assumptions. We have to blindly, we have to assume these things when we are performing this test. And when we are performing this test, we have to explicitly call it out that these are the assumptions which we have considered. Based on that only, we are inferring to this kind of conclusion. And the population variances are known to us. So for example, sigma x square, x is one sample, y is one sample. These are the two samples and the variances are known. And we are saying both the populations are normal, then the variance of 1 and 2 both together, okay, is given by this particular formula. So do not by heart the formula, guys. But I want to show that for different scenarios, the formula may change. Okay. So here it is sigma 1 square by n1 plus sigma by n2. Now this is my in combination of both the population, this is my overall variance. So you have seen, right, this problem. I'm taking both the samples, both the population together, and then this is one single distribution, which I'm kind of assuming. Now for this distribution, the sigma square is equal to sigma 1 square by n1 plus sigma 2 square by n2. Okay, where the sigma 1 square is the variance of population 1 and sigma 2 square is the variance of population 2. So this is how I'll calculate the sigma, and the formula of Z is this. Okay, it is the difference of these two sample means. Okay, this you can ignore. Okay, this will further confuse you. Just you take numerator as x1 bar minus x2 bar. That's all. Divided by this variance. Denominator, we are taking the standard deviation. That's the reason we are taking the square root of this particular variance. Right? So this is the formula. So just you remember that there is some formula to calculate the test statistics for this particular scenario. That's once it is calculated. So this is the formula. Okay. Again, you can ignore this. Okay, for now, just take this particular formula and then go and uh, calculate the probability values for that z value, and then based on that probability you have to go and infer whether you have to go with null hypothesis or you have to go with the alternate hypothesis. Okay, now this is how you can frame the hypothesis. Here we are saying actual mean of population 1, which is denoted as mu1, is greater than actual proportion of actual mean of population 2, which is mu2. So mu1 is greater than equal to mu2 will be the null hypothesis. Opposite would be my alternate hypothesis. So here, whatever we are inferring about the population, right, from the sample. So as we do not have this mu1, mu2, we will go with the sample means. Okay, with the sample means. And so with the sample mean, we will infer either the population means are greater than or less than or equal to the another population. Okay, so either you can represent your hypothesis like this, or else you can represent your hypothesis like this. To take this mean this side, then it becomes mu1 minus mu2 greater than equal to 0. In some of the books, hypothesis will be represented like this. Some of the books, hypothesis will be represented like this. So you should not get confused. It's just like this mu2, they have taken to the left-hand side and they have represented in this. Okay. Similarly, this, you need to concentrate on this particular sign. Based on this sign, you have to consider whether it is a lower tail or upper tail or a tail. Okay. I hope you don't have any questions on framing the hypothesis, right? Now, again, the decision rule will be the same. If it is a lower tail test, then your Z value will be on the left-hand side, and then you will take this particular region and that you will compare with alpha. If it is the upper tail test, then the probability value will be this. To calculate this probability value, we will take probability of Z and then subtract with -1 or subtract by 1. Okay, that will become this particular region and that you will compare with alpha. In this two-tailed test, you will divide this alpha on either side, and whatever probability you will get, either you compare with alpha by 2 or you go and multiply that probability by 2 and then compare with alpha. Okay. Now, let's take the example that would help you out. So with that, after this example, we will close it because I don't want to discuss even further on this because that will further confuse you. So we'll stop at this example. Okay. So now, 1 second. Rahul. Sorry. So here the product developer is interested in reducing the drying time of the paint. It's a paint manufacturing company. So the whoever is the developer of that particular product, so he is interested in reducing the drying time, okay, of that particular paint. So he has come up with two formulations of the paint. So and they want to test it, and it is a very um, general scenario, right? Sometimes we have to pick any one option out of two. And So either the one which is running and another, a new process, and then you have to compare which process is what we find, right? And is also used a lot on the web analytics space also. So for example, your e-commerce is having a particular layout, okay, with the landing page, your website. Now you are getting some level of traffic, some level of number of people are coming and browsing through that particular page, and then finally you are getting some sales out of through this particular web portal. But let's suppose you have something in mind and you think that some creativity needs to be applied, and then you have come up with some other different layout. Okay, and this is a different layout. Now you cannot just go and abruptly go and replace this particular page with this particular page, because if it doesn't work, then it directly impacting your overall sales. Right? Even the people, if they not like it, they will not come again onto your website. So it is quite risky. So what you these people do is in digital analytics, take they divert some percentage of traffic to this particular page and some percentage of traffic to this particular page. So let's suppose it is 50% or 50% traffic, they pass it to each of these pages. And here they will calculate the conversions or the number of the amount of time people spend on this particular website and the amount of time with this particular website. And then they will compare these two websites. Which one is more effective? So it becomes a two sample test. So they will collect some sample from this website, some sample from this website, and then they will compare. So similarly, in this particular case, they have two different formulation. Formulation one is the standard chemistry. Is the standard chemistry means it is the standard process which they are using currently. And the formulation 2 has here they have used a new drying ingredient, which will dry the paint quickly and which reduces the drying time. So from experience, it is known that standard deviation of drying time is 8 minutes. Okay. And this inherent variability should be unaffected by the addition of the new ingredient. So they're saying that the population standard deviation for both the population is the same. Okay, it's 8 minutes only. Now the test 10 specimens. So this is a sample size. 10 specimens from each formulation they have collected. Okay, from formulation 1 and from formulation 2. And overall it is 20 specimens. Okay, which are painted in the random order. So two sample average drying times are, this is my X1 bar where the paint 1 has been used and the average drying time is 121 minutes, and the paint 2 where they have used a new ingredient, the average drying time is 112 minutes. So here saying what conclusion can the product developer draw about the effectiveness of the new ingredient using alpha equal to 0.05. So this source of this is from this particular book, Applied Property and Statistics. Okay. Now here, you can take any kind of hypothesis. Okay, either you can take it as whether your here. I would be more interested that this mu2, which is drying time, is less than mu1. Okay, I want to prove this that new ingredient is really working, and the drying time is less than the drying time of the paint one. My This would be my alternate hypothesis. My null hypothesis would be just opposite of this and say it is greater than or equal to mu1. Okay, so this would be my hypothesis. Okay, so what I will do is I will go and calculate this z score. Okay, and that's z score. For that z score, I will go and find out the probability, and that probability I will compare with my alpha. Okay, and based on the alpha, I can go and make the conclusion. So here, basically, in this case, they have just taken sigma null hypothesis as mu1 is equal to mu2 and alternate hypothesis as mu1 is not equal to mu. Okay. And they have taken the conclusion that there is an evidence of the difference in means. They are saying that yes, there is a difference which is not equal to. But you can further go ahead and then you can use the lower tail test to further prove that whether statistically the mu2 is less than mu1 or okay. That's something, take it as an exercise. All right. So here I will stop. Okay. Um, so we will again quickly revise tomorrow this particular example, and then we will continue from here. Sure. I'm getting a call from office, so I have to drop off, guys. Thank you so much. We'll connect tomorrow.
Okay, sir. No,
Have a nice day. Bye bye.
have a nice day, sir.